Thank you. So first of all, I would like to thank the organizers for the invitation, but also for organizing this wonderful meeting in this wonderful place. I'm going to talk about a topic that was mentioned in quite a few previous talks at this conference, namely, when does a closed convex semi-algebraic set admit an LMI representation, or is a spectrahedron? And, well, I'll remind briefly the basics, which we already mentioned, the necessary conditions, and then what I want to do, I want to go through some details of the proof of the sufficiency in dimension 2 to try to persuade you that it's not as mysterious as something people think it is. And then, depending on time left, to tell about some new developments which are joint work. So the new is joined with Dmitry Kerner. And the idea is to try to understand better the set of all positive determinantal representations still in dimension 2, but with the hope that it will also give us more insight for higher dimension. Okay, so the basic question, which already was mentioned several times, is, so let's see, is this the roughly? Oh, this line? Okay, yeah. So given C in RD, closed convex semi-algebraic set, we are asking for the existence of A0, A1, AD, symmetric, real n-band matrices, or maybe complex Hermitian n-band matrices, such that C is the set of all x's in RD, so that the corresponding pencil is positive semi-definite. So that's the basic problem, and I will always assume that the interior of C is not empty, and in this case we might as well normalize by 0 being an interior point, and then we also might as well normalize by taking A0 to be an identity matrix. Okay, and then we come to the necessary condition that again was mentioned in several previous talks in various forms. So necessary condition is that this rigid convexity, so C is a rigidly convex algebraic interior, which means that C is the closure of the connected component of 0 in the set of all x's such that Px is positive for a unique real polynomial of minimal degree n, and let us normalize as well by taking P of 0 equals to be 1. So that's algebraic interior. And of course, P is nothing more than just the equation of the boundary. So if you take the boundary of C and you take its Zariski closure, that will be just the 0 set of your polynomial P. So that's the algebraic interior, and the rigid convexity means that where P is an RZ polynomial, meaning that for all x in RD, all the roots of P of Tx equals 0 are real. Or, as again it was discussed in several previous talks, this is just the same as saying that if we take a generic real line L through 0, then L intersects this real algebraic hypersurface, this is the risky closure of the boundary, in n real points where n is the degree. So, of course, there will be some exceptional directions where some of the intersections will degenerate, it will be tangent, or some of them will run off to infinity, but for generic straight line, you'll have exactly n intersections. Well, in a slightly different terminology, of course, if we homogenize our P, so if we pass to homogeneous coordinates, then this just means that P is hyperbolic in the direction 1, 0, 0, and again in this homogeneous language, C is the hyperbolicity cone, or more precisely, if we take the set of all points T, Tx, where T is positive and X is C, this is hyperbolicity cone. Of big P. Okay, now there is a geometric picture here that was again alluded to in several previous talks. How does such a hyperbolic polynomial or such a real zeros polynomial look? Well, it is isotopic just to if this hypersurface is smooth, if this real hypersurface is smooth, then it is just then the whole picture is isotopic to this joint union of n over 2 concentric spheres. So there is this picture, and as Bernd has mentioned, we should make sure not to draw these things convex. So they just nest around each other, and the fact that this is so, that it's always isotopic to this, follows by a theorem of Nui about the fact that the space of hyperbolic polynomials with a given hyperbolic direction is connected. And by the way, from here you see immediately both the fact that the interior component is necessarily convex, and another fact that if you take any point in the interior component, then it's still the real zero condition with respect to that point will be still satisfied. And the point is simply because if you take any point in this side, then for topological reasons, so you have n over 2 ovaloids here. So that's for the case of n even. For the case of n odd, there will be an additional component. For topological reasons, you will just have n real points of intersection, and you cannot have any more because the degree was n. And for the same reason, you see that it is convex, because if you take 2 points on the inside, and if you take a real line through them, then already here and here you have all the possible points of intersection with the boundary, and that means that this interval has to be on the inside. This picture implies, and okay, this is in the non-singular case. In the singular case, what happens is that some of these